Hello. So I'd like to talk about profile-guided function layout, and in our toolchain, the PS4 toolchain, which is based on LLVM. So when I talk about function layout, what do I really mean? And by function layout, I mean the order in which functions are placed in your final binary or in memory, in your process memory. Now, the default order that you get is based on the order of functions in your source code and on the order that you pass object files to the linker. Now, this order is better than a random order, but it is not necessarily the best order. And it's generally a good order because, or an okay order, because functions that are in the same translation unit are likely to call each other, and functions in the same library are likewise likely to call each other, and thus you get some locality, but you don't get the best. And so why do we want to perform function layout? Well, we get, because we want performance, and we get that from the way that modern processors work. The first is from instruction cache. And we don't want cold code in cache along with hot code, because we effectively reduce the size of your cache, because you've got all this cold code that you're not actually running. Now, most functions are larger than the size of a cache line, and so you're not going to be able to fit multiple functions into a cache line generally, but you still get some benefit here. The next, and is actually a really important one, is your ITLB, or Instruction Translation Loci Buffer. Now, this is a part of your processor that maps from virtual addresses to physical addresses. And a miss in the ITLB, or the instruction cache, means that you stall your front end. And when you stall your front end, you can no longer extract all this work, and it slows you down. Now, the ITLB is generally, the entries will be like 4K or 2 meg or larger. And you generally can actually fit multiple functions on this, or in this. And so what you can do is put a function and the function that that function calls into the same page. And so you're not, you reduce the number of entries you need. So let's take a look at the design implementation of this infrastructure. So there's 3 stages to this. And the whole goal is that the linker needs to know what order it should put functions in. It really has no clue what parts of your code call other code. Like, it can look at relocations, which can help a little bit, but it doesn't know which of those edges are hot, which are cold. And so to do that, we need to profile. And so for profiling, you use the existing LLVM profile infrastructure. And so this includes, you can use perf and do sample-based profiling, or you can use our front-end instrumentation or IR instrumentation. And as long as you get a profile, then this will work. The next step is that we need to extract this profile, because the profiles come in, they say this basic block is hot, or this edge in the basic block is hot. It doesn't actually say this function calls this function. So then we need to extract that information into which functions call which functions. Then we embed that into the object file, and then have the linker, in this case LLD, lay out based on that profile, that call graph profile. Let's take a closer look at these steps. So in the first step, profiling, this is just your standard LLVM PGO workflow. If you're doing PGO today, then this just works, nothing needs to change. The next step is to extract. And in here, we need to tell the linker about the profile in a way it can understand. And linkers don't know about functions. They only know about sections, symbols, and relocations. And so to extract this information into that form, we first have a new LLVM pass, the CG profile or callref profile pass. Now, sadly, this only works with the new pass manager. This is a module pass, which depends on a function analysis, and this breaks in the old pass manager, as the bot so kindly informed me when I leaked memory. There are ways this can be made to work in the old pass manager, but it's not really worth the effort. We're pretty close to moving to the new one, and so I just did it in the new one. What this pass does is extract the weighted call graph into module metadata. And it does this by just looping over all the basic blocks and all the instructions and the functions. Whenever it sees a call, it asks, hey, how hot is this basic block? and writes this into the metadata. This pass needs to run late in the pipeline. Basically, it can run after the last pass that modifies the control flow graph. So this includes, I think, after things like function merging. And if you're doing LTO, it needs to run like after LTO. So let's take a look at an example of what this pass does. In this LLVM segment here, this module, there we go. We've got external function B and a function A, which calls function B and has some profile data. The actual profile data is at the bottom as metadata. Then we have a global function pointer foo and a series of declarations of possible functions it could call. Then in freak, we have we do a call of that function pointer, and then based on a condition, we call one of two other functions. And so down at the bottom, this is just standard LLVM profile metadata, and it says how many times we enter the function. It has the branch weight information, so we know how often we call A versus B, and then it also has value profiling information, which you can get, which helps with indirect calls or virtual calls. And from this, we generate the following. This is LLVM module flags metadata. And this is a list of triples, which just say function A calls function B 32 times, and the rest. And these numbers, these do end up being absolute numbers if your profile is exact. But it's not required that these are precise absolute numbers. It's just the relative numbers compared to everything else is really what's important, and that accurately represents how your program executes. But the linker still can't read this. It can't read IR metadata, so we still need to get it into a format that it understands. And to do that, we have MC write this data into the object file. And for this, we've added a new ELF section type, LLVM call graph profile. And so currently, this only works with ELF. It's not hard to extend this to Coff and Mach-O, but that just hasn't been done yet. And so this new section, is a list of weighted edges between symbols. And we do this because we rely on the normal symbol resolution and merging to resolve to the actual section containing the code, which is really what the linker wants to know, is what order would we put the sections in, and so this gets us there. And this gets written out into the ELF assembly, and just looks like this. You can actually write this too, like added parser and dumping support for it. It's a pretty direct translation. Now, once we actually have this, the linker has it. The linker needs to do some layout. And so for that, we need a layout algorithm. And there's actually a great paper by Otoni and Mayer from Facebook, which describes the call train clustering heuristic. And so the goal of this heuristic is to find a good layout, but it does that by forming clusters of functions. And it does this by looking at call chains. And so now that we have this call chain profile, it says what function calls what function, now we can use that to form these clusters. And the main intuition of this heuristic is that we want to minimize the average distance between hot calls and their targets. But we need to do this while obeying some constraints. When we're forming clusters, we don't want to create too huge of clusters. Or we have a cache hierarchy. We're starting at like their 64-byte cache lines and going up until pages and whatnot. And if you make like 1 gig clusters, you're not getting any locality benefits here. And so you do need to restrict clusters. And currently we restrict it to about 1 meg in size, which seems to be a good fit. The other thing is you don't want to reduce what they call the density, which is how hot is this function divided by the size in bytes of the function, which is one of the reasons that this tool is done in the linker, is because the linker knows what size functions are. The front end and earlier parts don't. And we then perform a single pass over clusters, starting at the highest density. And at the beginning of the algorithm, every section is its own cluster, and then it forms bigger clusters as it combines them together. We merge good hot cullies, where good is things that meet this metric. And If they don't, we'll look for other places to combine, to merge them into. We then sort all the clusters by density. This then, instead of having a bunch of different sections or groups, clusters of connected calls, we now have those little clusters, but then we also take all the hot code and shove it to one side. Now this algorithm is actually pretty fast. It takes about 40 milliseconds for a graph of 35,000 functions and 115,000 edges. And it scales, it's a little worse than in login, but it's not in squared. So let's take a look at how to actually use this. So we need to go through our steps. And first, we need a profile. And to do that, in this example, I'm going to use the fprofile generate. And we also need to use the new pass manager, because this pass only works in the new pass manager. And right now, we're only profiling, so we're not actually doing the extraction here. But we need to compile the code the same way. Otherwise, your profile might not be correct or as accurate. Then you can link, and you can actually use any linker here, because we're not doing layout at this step, we're just profiling. Now you need to profile your program. Now here we're just running the program, but this is actually a huge talk on its own of how to actually accurately profile your program. Then you need to merge the profile data and get an actual prof data out. Now you can actually optimize, and so you're re-optimizing with the profile data, so you're doing normal PGO, but you're also extracting. You do that, you just compile, and that's it. There's nothing extra you need to do. And then finally, layout. We just pass the object files to the linker. This time it does need to be LLD until people add this to other linkers. And once you've done this, then it's done. It's correctly laid out. And you'll notice that this is actually the exact same steps that you would take to do a normal PGO build. There's nothing special here. Because of the way that it's architected, putting the profile data into the object files, it just falls out of normal PGO. So let's take a look at some results. So this is a PlayStation 4 game. We have several different, we'll do different scenes. And what this represents is on the vertical axis here, we have how much faster is our average frame rate. And this is the time that the CPU spends working on the frame, not the time that the GPU spends. So this is until we call submit and then wait for the next frame time to start. And so this is how fast is this compared to a normal 03 build with no PGO. And the blue line is if you enable PGO, but don't enable layout. And the red bar is with layout. And so you'll see there is quite a wide variation in how much this helps, even in in the same application. And we get from about 3% on the low end up to 7% in this middle one. And for this game, the numbers are actually very stable. It's like 0.5% variation run to run. Because of the way our hardware works and the way we have our system set up, we have the games can get dedicated cores, so there's nothing else interrupting them. Oh yes, and this binary, the whole binary is 32 megabytes, but it's about 17 megabytes of text or code. So why do we get this improvement? And this was a really interesting thing, is looking into well, how can we reason about this? And the first was actually a large reduction in ITLB misses. So here are the results from one of the runs, and what this is on the vertical axis, it is the number of 4K ITLB misses per frame. So this is across approximately 7,000 frames. And these are violin plots, and so the width here is how often did that number come up. And so you'll note that what's interesting here is that between the control run, which is just 03, and PGO with layout run, there's actually almost no difference. It's about 1% faster, but that number actually run-to-run variation here, it's in the noise. So PGO normally doesn't actually help with ITLB at all, but that makes sense because we do basic block reordering based on PGO, but that's just in a single function, and so you're not really going to see any ITLB benefit because ITLBs are pretty big. Now with layout, we shrink the whole thing, and it's actually about by 16% reduction in ITLB misses. So the other reason is reduce the instruction cache miss rate. If we look here, we can see that PGO actually does help with instruction cache miss. And that makes sense. We're reordering basic blocks, which functions are generally small, and so we actually can keep a single function, like a single loop, within a single cache line, or reduce the number of cache lines it touches. And there's about a 15% performance improvement here with just PGO. When you then move to layout, we actually do get an additional benefit, even though we're still bringing, when we move functions around, we're still moving cold code with them, because we're not like slicing functions yet. But we still do get about a 7% reduction. Now, there is some future work that needs to get done to improve this. And there's actually been some more recent papers that have explored more different ways of doing layout. And one of the things is we can improve the clustering heuristic. I have not spent a huge amount of time doing that. I did some scans over, like parameter sweeps over some things. But there's both the max cluster size, this 1 meg number, that really has only been tuned for like one target. That needs to get tuned for multiple targets, and it can depend on the target, especially if you're like not x86, then your numbers will be different here. And there's also this cluster quality degradation thing, and that's the how much we're allowed to change the density or the hotness divided by size of a cluster when we merge them, which also needs to get tuned. I don't know how big those changes will be. I don't expect it to be huge, but there's like an additional % there maybe. But the major thing is actually function slicing. We really want to separate out cold basic blocks. Because when we're moving these functions around, we're also dragging all the error handling code and all the exception code and just cold code. And if we actually slice functions before we do layout, then we can actually separate the hot part of the function and the cold part of the function into separate parts of the binary. And additionally, we can do things like separate out hot blocks with different callees. So for example, if you have a function which has 2 hot loops in it, which are both calling different functions, then currently this algorithm will just put those 3 functions in a line. And so you'll end up with one of the loops and its callee kind of far apart. And if we can actually slice these up, then we can directly put the loops next to the things that they call. And with that, are there any questions?
Thanks, Mike. We have a microphone set up in the middle if people want to line up there, or I can run the handheld to you. Go ahead.
Hey, thanks for the great talk. I was wondering if you did any work to measure any change in pagins over the course of your benchmark run?
In pagins?
Right, so what happens, I know you've measured reductions in ITLB and cache miss rates. What happens to memory utilization?
I've not actually measured total memory utilization. I expect that, there's no effort here done to deal with code that is never called. I think some of that falls out partially. You might see some reduction, but that's not an explicit goal of it, and I haven't measured that.
Thanks.
Tristan.
For the results without your new layout, but with PGO, did you do function sections so that you have the hot functions and so the hot functions were all clustered there and the cold functions were clustered?
Yes, they should have been because of because we do mark which hots. So yes, that did have, it was function sections and it did have the hot markers, yes.
Any thoughts on how we can do this for data?
For what?
For data.
Data. Okay, so the problem with data is that you don't have calls. So we're actually what we really,
right?
Yeah, so what we really want is actually the branch history trace for the entire run of the program. Because that actually tells you when are things hot next to each other. We don't actually know, just because 2 things are hot, they may run at totally separate phases of the program. And so we have this proxy in the call graph, but for data, we don't really have any way. There's, you could write a profile that just instruments every load. But also, a lot of programs don't touch data very often, like the data section. They allocate memory and then touch that. So yes, you could do this from data, and actually I looked into that because some people were asking about it. But I would need like a profile for it. And the current architecture actually would just work for that. In LLD, the optimizer there would just work. But
interesting talk. Can you say anything at all about whether the results look very different if you're in a sampling-based profile, you're using auto FDO as opposed to instrumentation-based profile?
I haven't actually tested sampling-based. I don't expect them to look different. So the other people, so this was originally based on the work from Facebook, the C3 thing, and they actually did sample-based. And Bolt is using sample-based, and they see similar improvements. I don't think that the it's coarse-grained enough, especially because it's calls, that the sample-based I expect would work.
I wonder how much of the gain remains if you only use static profile.
If you what?
Only do you use static profile, no PGO.
Where are you getting the static profile from? From just the call graph of the program. You could try that. That's you could do the same thing if you just use relocations. And I believe that someone from Google, I think it was Peter Collenborn, actually looked into doing just relocations. I don't know the results of that, though. I think at the time the original algorithm was in squared or in cubed or something, and I think he hit that problem when trying to pass every relocation to it. But the algorithm's actually much better now, so you could try that again. But I haven't actually looked at that.
Any further questions? Okay, thank you, Michael.